Thank you, everybody, to take the time to visit us here on this webinar. I see some familiar faces, some friends, so that's good. For those of you who don't know me, I'm Guillermo Valenzuela. I'm the VP of Sales and Marketing for WiseCon. I've been in the company since its beginning. Been working for about 15 years now with irrigation technology, soil moisture sensors, and overall irrigation management. Moved my family to the US in 2015 when we opened the office of WiseCon USA, and been here in California for the last 5 years, trying to spread the seed. And it's been a good ride. In general, we have had a really good experience. We've seen how this technology, soil moisture automation industry has boomed in the last couple of years, 2 to 3 years. So I've been able to witness that, and with that, those years of experience, I've come across a lot of people asking about how to use the soil moisture information, how to better use the automation system, what considerations to have. So we thought with Daryl to put together this, this webinar to talk a little bit about soil moisture, how to use the data, the different sensors that are available, maybe answer some questions. It's a very broad topic. So we're going to try to cover as much as we can in an hour, but I invite you guys to just send me an email. There's my email, g@wisecon.com, or just get in touch with Get Daryl in case you guys need a one-on-one. You guys want to go over your specific data, have specific questions, just don't hesitate to contact us directly, and we can put together a meeting. I'd like to call it kind of like the doctor's appointment, where we get together and spend a couple of hours looking at your data and see what happened during last season and get ready for what's coming on the upcoming season. So we usually don't have those kind of meetings during the winter. So if any of you guys have any time or are interested in going deeper into your information, don't hesitate to contact us. So I'm going to start off just talking a little bit about drop control for you guys, for those of you who don't know it. I'm going to be very brief about this so you understand how soil moisture connects into our products and our platform. Drop control, it's an online irrigation management system. It's basically a reliable irrigation monitoring and control system that's able to connect to any sensor, operate wireless valves, pumps, and fertilizer injection systems through an easy to use online software. So how this works is very simple. We deploy units through the field, usually called nodes or RTUs, remote terminal units. These RTUs have sensors connected to them, which can be weather sensors, soil moisture sensors, what we're talking about today. But it also connects to pumps, reservoir level sensors, wells, well pumps, flow meters, pressure transducers, you name it. It's pretty flexible in the sense that it can connect any sensor with an open protocol, and it can be used, all that data is used in order to perform better irrigation management. Then these RTUs communicate themselves through radios in the field in order to gather all the data, and then through one of them, which we call the gateway, has a cellular chip on it, will send all the information into the cloud to secure server played on the app or the web page, or even through an API can be taken into third-party software, and I'm going to later. So we consider ourselves to be the remote control of irrigation. This is a metaphor that I use because it's an essential part of the irrigation system. It's one of the lower cost parts, the cheapest part of the irrigation system, but it's crucial. The remote control allows you to, switch, pause, play, program remotely, and that is what drop control does on your irrigation system. So the main features is that we have cloud scheduling. You can schedule it from your phone. You can also run locally. If you have a switchboard or a Bluetooth enabled device, you can control it locally. And the main features, and I'm going to run through this very quick, but the main features that we have that we most commonly see out there on projects is the pump start stop feature through the system, flow meter monitoring to confirm what's going on, if the pump's running operating correctly, and to do water balance based on what we're irrigating the crop. pressure before and after filter to check on our filters, if they're flushing, if they're clogged, if there's any problems with the filters. Groundwater level monitoring, especially for Sigma and other regulation requirements. And other than that, we do reservoir level monitoring, fertilizer tank monitoring, filter flushing is coming out soon, power monitoring, so how much energy the pump's pulling in order to run a pump test every time we run it. So overall pump control and monitoring. And then in the field, we open and close the valves, hydraulic valves operated through solenoids, and we deploy sensors, usually pressure switches or pressure transducers that will give us feedback of the valve operation. We are also involved in the fertilizer injection, monitoring electric conductivity and fertilizer injection, controlling the pumps that inject the fertilizer from the tanks, and acid injection in case you're using this for pH control that can also be tied into a pH sensor on the pipe and run a control cycle in order to maintain a pH on the water. We also have weather, of course, a crucial part of irrigation. We put weather stations. We're tied into CIMES. We're tied into other, common weather station brands through APIs and other methods. We also have weather sensors that are locally installed in the field. That way we can get all the rainfall information, temperatures, frost alerts, and of course, for irrigation purposes, ETO that we're gonna see in the upcoming slides. We also have incorporated plant sensors. This is for some growers. Some growers are more advanced on their management or in specific practices, fruit growth sensors, dendrometers, NDVI on the plant, leaf temperature through infrared sensors. We've seen guys deploying in order to manage their irrigation better and add more information into their decision making. And finally, soil moisture sensors. Soil moisture sensors that give you basically the moisture in the soil, temperature, and salinity in some cases that allow us to understand what's going on underground with the water, with our irrigation, and how the water is moving in the soil. And this is what we're going to talk about today, soil moisture monitoring. That takes me to the topic that gathers us here today. First thing around soil moisture monitoring is what is the objective that we want to accomplish. I like to say that we want to basically have a continuous auger. We want to be able to have a place to look at what's going on the soil, what's going on with the moisture in the soil on a continuous basis. So we can take that manual hand feel of soil moisture into a dashboard software that allows us in a simple manner to see where I'm at. You can see on the right-hand side, we have a map with different blocks. It's got 6 soil moisture sensors. 3 of them are very wet. That usually happens right after an irrigation has been done. We got 1 of them that's on the dry side that hasn't been irrigated or it's the soil is dry currently, and a couple that are in adequate conditions. So main objective is to be able to take that auger that they were probably doing in the field and checking moisture with an auger and taking it into a software-based continuous reading. There are different types of sensors, and there's usually confusion around this and which sensors to use. So mainly we have 2 families of sensors, the ones that measure volumetric water content. So those are usually the capacitance probes known in the market, and then water potential or tensiometers. So one's monitoring what is the amount of water in the soil, the other one's monitoring vacuum pressure in the soil. So it's 2 different technologies, 2 different methods to get to the same result, but they are used differently. And there are people that are, tend to use more one than the other, and there are, people have one preference over the other. In general, I don't want to talk about the technologies and see which one's better or which one's not. There are pros and cons on both of the technologies, but what I can say is that there is a direct correlation between water potential and volumetric water content. So this is either technology that you use, you're going to get to the same objective. The important thing is that you use the technology correctly. Now, to talk a little bit about them, First, I'm going to touch the tensiometers and gypsum blocks, water potential or tensiometers, which I'm briefly going to talk a little bit about them. The first one is the tensiometer. A lot of you must know it or might have used them. They are very popular, have been around for a long time. There's a lot of documentation around tensiometers. And the main pro on tensiometers is that they work on the same scale for any soil type. So if you're working on that 10 to 100 centibar scale, regardless of your soil type, that's always going to be your scale. So it's pretty straightforward to understand the reading. How we connect to this tensiometers, that pressure gauge, it's basically transformed into a pressure transducer that will give us the pressure continuously into the node or RTU, so we can continuously be reading the aerometer every 10 or 15 minutes. The problem with the tensiometers is that they're labor intensive. You got to go out there and fill them with water. You got to be constantly handling them and making sure they are operating correctly. So the continuous objective there, if they run out of water, then you stop getting the reading. So the data gets inconsistent sometimes. Some companies have solved this by developing continuous water potential sensors through gypsum blocks, or the one in the bottom, that the MPS6 by Meter Group, which is a water potential sensor based on a capacitance technology. But there are only a few sensors that are doing this. And what we've found and the experience we've had is that they're very sensitive to some of the soils, especially on clay soils. If that clay soil dries out, then those sensors deattach from the soil, and then you got to reinstall them. There's no way to get them back there running how they should. So again, the continuous objective of reading soil moisture gets affected, or it's inaccurate. And then finally, we find the ceramic tips that we've seen on some of the solutions out there. There are a couple of good alternatives today. Alternatives are in the market, are closed platforms that only operate with their telemetry, a closed-based database, no API, no integration. So it's very hard to scale and get to broader objectives by using the sensors. Again, this is our experience and what we've seen in the market and what we've tried. We are not against water potential sensors, but this is some of the ifs that we found. But we have several, if not 100 water potential sensors installed in the field currently, data logging through our system. Now, but again, I'm going to focus on what our experience has been, and that is on the volumetric water content sensors, specifically on the capacitance probes. This is where we have most of our experience. We installed south of 1,000 a year, and we have a lot of data sets and a lot of experiences, and this is what we've been using. So it's what we can talk about with more property. TDR is another technology used for volumetric water content. It came before the capacitance probes. Capacitance are actually FDR. TDR stands for time domain reflectometry. FDR stands for frequency domain reflectometry. The reason TDR did not go massive was basically because of pricing. Equipment usually was high value sensors. It required field calibration, and it was sometimes affected by salts in the soil. So there was high salt content. The TDR readings would have to be calibrated, which made it difficult to have any grower use it on a continuous basis, again, which is the objective. So that was solved with the FDR technology, frequency domain reflectometry, and most of the cases are presented as probes. So they are probes that are inserted in the ground, like the picture that you can see now, that you auger a hole, you install the probe, and the probe is installed there and measures through vertical horizon on moisture. So I was saying FDR's frequency domain reflectometry is basically reading frequency, and the sensors have an electric field around the sensor itself that is basically measuring what is the percentage of water. So this sensor reads, the reading is related to the dielectric constant, and the dielectric constant of water is stored to 1, and the dielectric constant of air and soil, it's towards 0. So there's a direct correlation between the reading of the dielectric constant and the amount of water present on the area of influence of the sensor. Usually these sensors vary on what their area of influence are. Some are broader, some are smaller. That is actually a very important aspect to consider when choosing a soil moisture sensor. But overall, the concept is that you have about a 10 centimeter square around the sensor itself, and with this electric field, the sensor is basically telling you what is the percentage of water in that piece. The rest is air and soil. So it allows us to understand on what range we are on our soil moistures, that we're towards the dry spot, we're towards, you know, a field capacity, or are we on saturation? Basically what happens here is that when you are on a dry soil, you have air pores with air, you irrigate, you fill those air pores with water, and all that air turns into water. So your water content, or volumetric water content, goes up. So as I was showing before, the probe is installed next to the tree, and it allows us to understand on different depths what is the percentage of water compared to air and soil present right next to the sensor itself. And we see, of course, there's challenges, as we can see on the right. You know, the water bulb is what we are potentially getting out of these sensors, but we can see those water bulbs vary from a sandy soil or a clay soil. Of course, they vary in shape based on the porosity. The infiltration rate varies. So it is very important to understand when we're reading the soil moisture sensors, what kind of soil we're working on these capacitance probes, what kind of soils we have, and what kind of soils we're working on, in order to understand what kind of water bulb we should expect. So what do we get from these sensors? It's a volumetric water content. So the first thing we can see is irrigation events. When there's an irrigation event, and I don't know if you guys can see my cursor here. I can have a pointer. But basically, every time we have an irrigation event, water content goes up. So this is an irrigation right here, and then this is percolation, and then you start with the water content or soil moisture depletion. So after several days, there's another irrigation event, and the water content comes up. So the first thing that we can clearly identify with these capacitance probes is irrigation events when the curve goes up, opposite as people that might be using the tensiometers or water potential sensors. When there's an irrigation, content comes down towards 0. This is read the opposite way. There's an irrigation event and water content comes up. So there's more water on the soil, less air. So first thing we get is irrigation events. The second thing we see are the daily drink or daily dynamic of evapotranspiration. What we can see here that looks like staircases is basically the day and night dynamic. So there's the percolation, then the day comes, then the night, then the day, then the night, then the day, then the night. So we can clearly see the daily drink of the tree, of that plant. We see that there's root presence. We can see how deep the roots are and how active the roots are. We can see how deep my roots are drinking water based on which of the sensors are presenting daily drink or root activity. So we can clearly see irrigation events, we can clearly see root presence, and we can clearly see root activity or water consumption. Now, as I was saying before, these sensors have different depths. So what we get here is, a sensor every 4 inches is usually what a lot of people is using, and what the standard of, in this case, the CENTAC probe drill and drop has is a sensor every 4 inches. So what we get here is that there's an irrigation event, and what this sensor is giving me in this case is giving me infiltration depth and infiltration rate. So I'm able to see how deep the water got. In this case, we can see the water got all the way down to 26 inches. And I can see how fast the water got there. So I can see how long it took between I started my water and it hit that 6-inch sensor, and how long it took to go from the 6-inch sensor to the 26-inch sensor. So I can see clearly how many hours it takes from the minute I start my irrigation system till I get water down to my bottom depth. So I can see the infiltration depth, or how deep the water's getting, and my infiltration rate, how fast is the water getting. And on the other hand, as I was explaining before, I can see my root activity. In this case, I can see there's water consumption on my 6-inch sensor, on my 10-inch sensor, my 14-inch sensor. 18-inch starts lowering, but there's still root activity there. And at the 22-inch sensor, there's a little bit of activity. So I want to make sure those roots get water because they're drinking. And then down on the 26, I can barely see any movement. What are the probe alternatives that we have out there today? These are the most common. There are more, and there are constantly new coming out. But the first one that came out was the CENTAC probe. They've been around for a long time, 25 years, maybe more. And they were the ones that developed the capacitance FDR concept. Then you have EnviroPro, very popular, lower cost, 5-year warranty. It's a good solution. HSTI or HydroScout, also been around for a few years, also has a long-term warranty and seems to be having a good response from the market. Then you got AquaCheck on the right, which is a very common probe and used by a lot of telemetry companies out there, and a lot of growers have had experience with them. And then the Decagon or meter group sensor, the GS3, they have other models, but I would say this would be the one to go with, the GS3, that allows you to monitor moisture, temperature, and electric conductivity. Now, out of all these alternatives, we, as I said before, we're sensor agnostic. We have all of these sensors connected to our platform. We've used all of these sensors, but the one that we use is CENTAC. That's the one that we distribute. That's the one that we recommend. Although we don't have any problems with any other of the probes. If there's any other preference, or even a preference on another technology, as I said before, like water potential or tensiometers, we connect those sensors as well. This is the one that we have experience with, that we can help. We know more about them and maintenance-wise. We know them, how they work. And the reason why we recommend it is because of the accuracy of the data. Data is very accurate. We've had probes installed for more than 10 years. The installation method that they have is very unique. You know, it's they have installation tools, and they have installation methods that they recommend, so you don't have to do slurry to install the probe in the ground. The durability, as I said before, we got a probe for 10 plus years. The unique design, the EnviroScan and the drill and drop are two probes that have their own unique design and their own installation method. The drill and drop is a tapered shaped probe that comes with a tapered shaped bit for you to drill it in the ground. So there's immediate valid soil moisture readings. And finally, the experience these guys have in the market, being the ones that they started with this technology. They've seen a lot. They have thousands of probes in over 80 countries. So that is a good support that we always count on. And as I was saying, the installation method we've seen out in the market, this is probably one of the fastest and more accurate, reliable ways of installing the drill and drop. It's a tapered shaped probe with a tapered shaped bit. You install it in the ground. It's fairly quick, and you got valid readings from the beginning. So I don't know, Daryl, if you have any questions or anything before I get into how to use the data.
Yeah, so we got a question asking if it's possible that some of the root activity at the lower depths is due to moisture coming up from lower depths, if you know what I mean. So if moisture is wicking upwards.
Yeah, we've seen that, and it actually happens on the top depths as well. It's what's called the Duren effect, when the tree starts pulling the water up to drink it. But what happens there is that you don't see that phenomenon of the staircases. You actually see water content coming down and potentially even coming up on higher depths, but you don't see that staircase so clear by that water being pushed up. What you can see is that you can see maybe higher activity on a higher depth that you were not expecting because of that water coming up. So those kind of movements in the soil can also be recognized, but that very clear staircase shaped is mainly due to root activity and water consumption.
Gotcha. And then we had one more that asked, does water leak down along the sensor? Does water that is leaking down along the sensor affect the reading? So if there was
Well,
water right on next to the sensor?
yeah, and that's why I was talking about the installation method. What they're mentioning there is what it's called preferential flow. So what happens here, and I'm going to go back a little bit, what happens here with the probes, and this is a good way of explaining it right here. What happens on some of these probes is that when you do a slurry installation, and you drill a hole that it's whatever half an inch wider than the probe, then you insert the probe and you fill the gap with that slurry. The problem is that some of these probes, especially the ones that with smaller area of influence, they will only read an inch or an inch and a half outside of the tube or of the probe. So if you have an inch of slurry to each side, and you have a probe that only has a 1 inch area of influence, what you get is the reading of the water movement on the slurry. And that gets you to see basically preferential flow. I've personally seen that happen. So the way to avoid it, and that's why I was saying our preference is the CENTAC probe because of their installation method, because you don't have to do slurry with that bit. You like you can see in the picture, your probe gets in direct contact with the soil from the beginning without necessity of doing slurry. But the slurry is usually a case when you can see some of that preferential flow. And as I was saying, I've seen before a probe installed with the slurry. And again, the soil will adapt and will compact back together, but in a few weeks or months even. But so in the first few irrigation events, you got to be super careful on understanding that you're not looking at that preferential flow on that slurry. And the way to confirm that is basically going out there in the field and watching it. As I was saying, we had a probe and we could see that based on the irrigation, the probe was telling us the water was getting all the way down to 4 feet, but we went out there, augured, and the water was only getting down to 2 feet. Now, what's happening because that structure of that slurry was letting water by faster. So that is something to absolutely keep an eye on when you're choosing a probe and when you're installing the probe. And if you do choose a probe with a lower area of influence and that needs to be installed with a slurry, then you need to keep an eye on those readings for the first few weeks.
Gotcha.
Okay, so I'm going to jump into how to use the data. And again, I'm going to base most of this information on our webpage, dropcontrol.com, where most of you or a lot of you guys have. And you will view the data, so it's familiar screenshots and familiar information. So the first thing that we get when we look at the soil moisture graph is this chart right here. And what we're seeing here is, and I'm going to get back here for a minute because I did not read this. I'm going to discuss the sum methodology. So there's different methodologies around analyzing the data. There's people that do average on the different depths. There's people that normalize the different depths to a field capacity and available water levels. Those features are available on our software, but for time purposes and because of the percentage of people that actually use this methodology is that I chose to discuss the sum methodology. So the graph itself right here, we're looking at a graph. It's showing you on the top part, it's showing us the readings of different depths. So here in green, we got the 12-inch sensor. In purple, the 24-inch sensor. In light blue, the 36-inch sensor. And in brown, the 48-inch sensor. So we're basically talking about 1, 2, 3, and 4 feet. What we can see here on the top graph is the different depths. So each one of the readings is for each one of the depths. In the middle, we have our sum or added soil moisture, where we choose depths from the top and we add them up and generate the added soil moisture graph. And in the bottom, we have the ET in yellow, in rainfall in light blue, which we don't have any rainfall here, but in this graph specifically, but if there were, it would show in light blue, and in dark blue, irrigation. So the way we use this graph and the way to understand what we're reading and how we can use it, and I often tell growers, a lot of the growers use this to understand how deep the water got. So in this case, I can tell that this irrigation got all the way down to 48 inches. This one got down to 36, and water ended up hitting 48, but did not really irrigate that deep, as it did on this irrigation right here, where it hit both 36 and 48 inches. So a lot of the growers are installing these probes, putting them in the ground, and then coming back and tracking how deep the water got based on the sensor. Well, I tell them to turn that question around and ask, how deep do I want water to get with the sensor? And that's where that trial and error starts. So we determine the duration based on this top graph. This top graph allows us to understand how many hours of how many inches of water do I need to put in order to get to a certain depth. And that allows us to have a control bulb. That allows us to have a control root zone. It allows us to understand where our root zone is and where do I want to keep it. So I can control, and I can control the size of my root bulb by controlling how deep the water gets. So this top graph allows us to understand how long do I want to run, or do I need to run in order to get to a specific depth. Let's understand this a little bit better. So we have the sensor, and what we do is that we put a sensor, or we usually have a sensor that is underneath the root zone, below the root zone. So this sensor is going to be our alert sensor, because we know it doesn't have roots. There's no root activity on the sensor, but so we don't want to irrigate it. But if we start drying that sensor, we might be drying the top sensors where my roots are. So this is my alert sensor. If I'm spiking it, I'm irrigating too long. If I'm drying it, I'm irrigating too short and maybe drying my root zone. So that bottom sensor allows me to determine how long do I need to run to maintain the moisture on that depth without irrigating or adding water content to it that basically results in wasting water, energy, and potentially fertilizers. So that bottom sensor allows me to understand, and here comes a little game of trial and error. So you can see here on the top graph, I can see in light blue, those bars in light blue is the length of the irrigation event. So I can see here that on this irrigation event, that was a little bit longer. It was one event during the week in gray here. The different grays show the different weeks. This is the week of April 20 this year, April 27, May 4th. So we can see this grower, he did a long irrigation, one event during the week, and it was a long irrigation. He put out half an inch on one event. So the water got down all the way down to that, or more, it was kind of more like 0.65 inches. And the water got all the way down to the 4th foot. And then we can see that he switched that irrigation strategy to 2 times a week, shorter durations. So a cup, and it's still irrigating during the week, that 0.7 inches, 0.8 or 0.9 inches, but in 2 events, not in one. So we can see that the water hits on my 3rd footer and the moisture content stays flat on my 4th foot. So he basically, by that trial and error, he determines how long he needs to run in order to reach the exact depth that he wants to reach with his irrigation events. Here we can see that this was at the beginning of the season, and we had a lot of root activity on the 1st and 2nd foot, not a lot on the 3rd. Some root activity started happening during May, and now here in end of May, clearly the 3rd foot sensor was showing clear activity right now. So then he needed to bump up his duration a little bit. But here in this week of May 11th, we can see that there was a longer irrigation event, and he didn't irrigate for several days after that. And he got all the way down to the 4th foot where he has no roots, so he has no need to put the water down there. So a 1.5 inch irrigation event for him is just basically wasting water, getting the water too deep where he doesn't have any roots. So with that trial and error, I start putting hours, shortening hours, and understanding and hitting that sweet spot. I don't want to run too long because I don't want to hit that deep sensor. I want to run just enough to fill my profile. And that's what he did. After some trials and error, he ended up coming up with the result of irrigating 0.45 inches that allowed him to irrigate and get water to the 1st and 2nd foot sensor, get water to the 3rd foot sensor. This was before root development, of course, and then for the 4th level, maintaining the moisture. So that first graph on top allows us to understand how long I want to run. Then in the bottom, we have what we call the added soil moisture sensors that allows us to understand when do I need to run and what's the frequency of irrigation. So how do we do this? First thing is that, as I was showing you before on the case before, we have two depths here, the first and second foot sensors that have root activity. On the right-hand side, we have the capability of doing settings and adding the 12 and 24-inch sensors. And this one will automatically generate the added soil moistures. So now what we're looking at is a curve, one curve that is showing us the water coming in and the water coming out, or irrigation and soil moisture depletion for my root zone, for my complete root zone. And this now allows me to manage when do I need to irrigate based on the consumption of my tree at all different depths where there is active root activity. So we can see here that again, and we're not going to be looking at numbers. We're not going to be looking at specific numbers. That's one of the pros that water potential sensors have, where your scale is the same. Water content sensors have different scales and different numbers for different soil types. What might be a wilting point on a compressed clay could be field capacity on a sandy loam. So we're not looking at the numbers. We're looking at trends. We're looking at depletion rates. Here we can see clearly that in 3 or 4 days, the water got all the way down to half of my tank. But over here, in 4 days, because of phenology stage, weather conditions, different reasons, the consumption of the tree was much faster. So my soil moisture depleted a lot more in 4 days than it did a couple of weeks earlier. So now I'm looking at that. I'm looking at my tank and I'm looking at how fast that water depletes. And when it gets to that refill point, I start my water. So my added soil moisture sensor is allowing me to understand when I need to irrigate based on how fast the moisture is depleting on my active root zone. This changes and varies between different soil types, as I was saying before. On a sandy soil, it might take a couple of days before you deplete it all. On a clay soil, it might take 4 days to deplete your moisture. And then if we take a closer look, we need to understand as well if those consumptions are varying based on weather or are varying based on water availability. If water is available in the soil and there's a change in weather, we'll see that the consumption of my tree will be reduced when the ET drops. But then it will grow back up again when the weather heats up again or the ET increases. My tree starts drinking more. And that is because there is water available. So the reduction in consumption was because of a weather factor in this case. But being water available, the tree will regain its depletion rate or its consumption rate as soon as the weather kicks back up. Now, different scenario is when water is not available and you have the same ET, in this case 0.21 inches on the same day, but the dynamics are completely different. That is because there's no water available. That is because the tree does not have the capability of pulling any water from the soil, so there's stress. At the same ET level, no change in weather. The difference is on the first day, the water was right available, the day right after irrigation. On the 4th day, it was the day before irrigation, water was not available. And you can see that the same ET, completely different consumption rates, so you can differentiate between stress and no stress. So understanding this concept, how do I define when to irrigate? Well, as I was saying, we got our trends, we got our rates, and we can clearly see the consumptions in this graph. And then we can clearly see how the consumption stops after hitting that onset of stress. So when the stress starts, is when the tree basically does not have that available water and cannot drink anymore, even though your weather, your ET, your conditions, your phenology stage, everything is the same. The tree is not able to pull water because there's no water there, and the sensor is showing us that. And then, of course, if you let that go for several days, you might even hit that wilting point where you never want to get to. So this is the refill point where you want to irrigate. You want to, before starting the stress, and even when the consumption shrinks or reduces to a level where it's less than it's up here because of saturation, you need to irrigate and start this cycle back up again. Now, as I said before, there is also stress here on the top part. If we're irrigating too much and we don't leave any oxygen for the roots, then the consumption is low. So that's why we're looking at this process to be, harmonic and constant. We want to restart it and make sure that we are never on any of the extremes. We're never on too much water, no oxygen, or too much air, no water. We want to keep our trees always in that fairway. And this is what we want to avoid. We want to avoid water logging, water extraction reduced due to excess of water and lack of oxygen for the roots. And we've seen this happen. We've seen this where, maybe a grower waits too long to irrigate and then decides to irrigate, and by irrigating too much, puts too much water, thinking he'll buy more time, he'll have more time. But at the end of the day, there's several days, 2, 3, 4 days. In total, these two events were like 15 days that the grower had the plants in water logging, and they were not drinking until they got to that sweet spot, that full point, or close to field capacity, where the plants can start drinking the water and you can start seeing the dynamics. So you want to avoid that water logging as well, and reduce the days. Even if you're flood irrigating or whatever irrigation method is, reduce the days of water logging as much as possible, so you can get the most out of that, good water oxygen equilibrium in the soil to maximize water consumption. So what we want to see is something like this. We want to see our irrigations fairly even in time, the duration. Here you can see that the water started depleting, so maybe we want to add a little bit more water, maybe increase a little bit our duration to hit that depth, because the tree is drinking more water. And we can see how this is tending to reduce. But this is what you want to see. You want to see a determined duration and a determined frequency, which in this case, this grower is irrigating 0.45 inches every 96 hours. So that he finds that sweet spot. I know with half an inch, I fill my tank, and I need to refill it every 96 hours in this case. And that is what varies. That 96 hours is when it's going to change. Depends on weather, depends on, again, the phenology stage, how much the tree is drinking. The 96 hours might be less, might be more, or certain phenologic stages, you might want to keep the moisture high. So you want to be irrigating more frequently. And then when the fruit is set, or 30 days after the fruit is set, you want to cut back a little bit on the water, and you drop that refill point a little bit. And then all this combined with alarms that you can set on those thresholds, so you can get an alert, an SMS, or an email if any of your soil sensors are hitting those low points. And then we have the mobile app, of course, that allows you to look at the data. In this case, I'm not going to go in detail. It's the same concept, but we have the capability of viewing our added and our different depths on the app. It pushes notifications or alerts, as I was explaining before. And you have that map in your app that allows you to understand if you've already set those thresholds. You can quickly get into your app on the phone, look at your map, and see where your soil moisture thresholds are. In terms of considerations, I think this is very important in order to be successful with your soil moisture data. So I just threw some slides here to show you guys what needs to be considered. The proper installation is key. The fact that the probe is installed on the correct location, on the correct tree, on the correct soil type, with a nice clean installation, that is key. 90% of the problems that we have with probes are because of a bad installation. A wire was chewed, it was on the way of the tractor, it was too far from the emitter. Installation is key. And what needs to be considered is, well, first, know your soils. Very important to understand the soil types in your ranch and where you want to locate the probes, where you want to install them. And make sure that you choose the correct location, the correct tree. In this case that we're viewing here, the probe is right here, but this was a tree that has some growth problems, and they had to top it off. Compared with the rest of the trees on the orchard was not comparable. So this probe needs to be installed by a tree that is homogenic and is comparable to the rest of the trees on the ranch. And then the materials, of course, make sure there's no bare wires exposed for coyotes to chew. That is the most common thing that we see. Our distributors do a very good effort on installing that. Some of these animals just try to get through it. So it's very important to be checking on these probes, continuously checking the location from the emitter. If you have an emitter that is right under, the probe is right under the emitter, you're going to get a different reading than if you have a probe that's 2.5 feet from the emitter. So you're going to understand where your probe is to understand what kind of reading you're getting. And this is crucial to understand all this information and how the probe is in the field. And I tell growers, you know, when you're walking the field, try to walk by that probe, you know, once a week, check that everything's in order, check that that emitter is not clogged, check that the probe's working, that the wire's good, you know. Actually, on this case, we can see that in pink here, we have the irrigations, and we can see that there's no activity, or the irrigations don't show on the offset probe, but on the probe under the drip, you get every one of the irrigation events. And then here in dark blue, you get the rainfalls, and you can see that the rainfalls appear in both the offset probe and the emitter probe. So it's very important to understand just basically where your probe is and how far it's from the tree, how far it's from your emitter, to understand what kind of information you're getting on the software. The distance from the emitter is crucial. Here we have an almond with micro sprinkler. So the sensor is about 18 inches from the emitter and 18 inches from the tree. Here we have a probe on a citrus tree with drip, 5 inches from the emitter, 5 inches from the tree. So it's very important to understand that the probe needs to be where the water is. The roots are going to be where the water is. The probe needs to be where the water is. That way we can manage our water dynamics. Ground truth the data, also important. Especially the first years or the first season to use the technology. Go out there, auger, dig a hole. I've had growers that do it every Monday, and they go out there and they check on the soil with their hand, and they compare with the probe until they're comfortable and they believe the probe, and they're completely confident that the probe is telling them what the moisture levels are. And then add potential complementary sensors, you know, like the ones that I showed at the beginning, plant sensors, flow meters, pressure switches, other sensors that will complement ET, that will complement the soil moisture data for a better understanding. I got a couple of minutes left, so I'm going to run through some examples here, and then maybe we can wrap up with some questions. I'm going to talk a little bit about Fresno State. Fresno State was a system that we installed back in 2013, and when we got there, irrigation was based on an ET, and the timer was fixed to irrigate 0.2 inches every Monday, Wednesday, Friday, and Saturday. And this is July and August of 2013. You can clearly see, based on the irrigations, that everything, and there was a weather station showing us the ET, but the irrigation was flat and it never changed, fixed on a timer. What we saw on 2014, and we did a test, was that the second sensor, the second foot sensor, started drying there by the beginning of June. So we got in contact with the farm manager and we told them, hey, can you do a run in the next week or so where instead of running 4 times 0.2 inches, can you run 2 times 0.4 inches? So double the water, but in 2 runs instead of 4. And you can see that that frequency here changed from the beginning, and the water, of course, got deeper. We were just concerned that the sensor was not working. We usually don't tell growers what to do or how to do it. But in this case, we were concerned about the sensors. We wanted to make sure that the sensor was acting properly. And the trees reacted very positively because there was roots down at that 2-footer. So that took us to 2015, where the farm manager basically told us, hey, you know what, I want to use the sensors to run and irrigate. And that's what happened. So we ended up, through the same methodology that I explained before, determining that this 165 gallon per minute, a 20-acre block of olives, the decision was to recover at 0.35 inches every 20 hours, or 20 hours of runtime every 30 hours. Overall, the farm manager was keeping an eye on KC to maintain that 0.5 KC of ET was what he has been doing in the past. So we kept the same amount of water. What we were just determining here was frequency. And so he was calibrating that based on what he was getting. Overall, what we got is that they irrigated about 22.5 inches, about 1.87 acre-feet per acre. In 1,300 hours, 89 times the pump started with an average flow of 150 gallons per minute. And the KC ended up being about 0.52, the real KC, based out of the ET plus compared with the inches irrigated. And here you can tell a little bit of the story. First happened that in February, I remember I was at the farm show. This was 2015, and we could see they were irrigating. This was back in the drought, not a lot of rain. Soils were very dry. So the farm manager decided to put some water out there and simulate the rain since the canals had water. So he started the water and irrigate during February to put some moisture on the soil. Then we can see that the irrigation started about March 20th. And then when he started irrigating based on that, on this methodology and this duration and frequency that I explained before. And we were keeping the water very good at 3 levels all the way down to the 3rd foot. The year before, we had seen how in June that 2nd foot had completely dried out. So in the beginning, we were keeping the water all the way down to the 3rd foot, keeping that water level up. And then 30 days after the fruit was set, we cut a little bit back on the water in order to save a little bit of water. And overall, our moisture came down. The problem was when this added soil moisture started hitting the red line here, and I started getting emails. So I started calling him and asking him, hey, what's going on? You're not running enough. Oh, I'm running the 20 hours that we discussed, instead of 30 hours, we pushed it to 40, I think, but I'm running the same. I don't know why water's not getting deeper. And I can see my 2nd footer there starting to dry out. So in a desperate, so we could see first thing that we saw is that the flow went down. So it went from about 170 gallons per minute down to something like 90 gallons per minute. And on a desperate intent of solving it, he did a pulse irrigation and run 4 times in a day, which doesn't help really because those pulse irrigations keep the water shallow, not deeper. And we ended up finding that the flushing valve was stuck open. So he was losing a good percentage of his water through the flushing valve, like 30–40% of the water was going back into the reservoir. So he got that fixed, and we got the flow back up at 165 gallons per minute, and we were back on track. But that was a good example on how I just set that minimum line to send me an email, and we could find a problem in the field through the soil moisture sensors. And then after that, towards the end of the season, he gave me a call and he said, well, I'm a little bit small on size. I'm very interested in bumping it up a little bit, but I don't want to irrigate too much, so I don't fill them up with water because the dry content is very important for the olives and for the oil. So he did that strategy 1 month before harvest, and he put a little bit more water there. That first event, he went out with the concept of, I'm going to run 48 hours. And I told him, well, that doesn't do anything because you're irrigating that 3rd and 4th foot where you have no roots. So you're just wasting water. What you want to do is run more frequent. And that's what he did. So he got more water out there. We got a very good size without affecting the dry content on the olives. And that was a good news. So harvesting was in October. And then we came up and reinstalled the probes in the year after. Overall, what we saw, it was something between 10 and 20% less water. Used 23 instead of 28 inches. About 10 acre-feet were saved, but the main thing to see here is that the 2nd footer never got this stress that we saw the year before. So that 2nd footer never got to stress out. You can see here, it was with less water, we kept water all the way down to the 2nd and 3rd foot. And up until, July, mid-July, where we cut a little bit of the water on it, but we never lost water on our 2nd foot sensor. And we used less water. The only thing we changed was frequency. This is the timer. You can see how Monday, Wednesday, Friday, and Saturday, and he was based out of the requirement. Overall, production increased in 33% in olive oil. Then the next year, it went down a little bit. Then the year after, it went up again. So now they're doing the technique of topping off those trees to try to hit the 4,000 gallon of oil line every year. So they're also now with irrigation controlling the year effect, the on-off year effect. And investment-wise, this was a project that was about $15,000 investment, ended up recovering just on the production side of things, everything in the first year. But he did say that it saved him about 3 hours a week, not having to go out there and irrigate manually, and he did save some of the water and energy. fairly quick. I don't know how we're on time, Daryl. I think we hit the time, but I'm going to take a couple of minutes just to show very quick examples that we also have on some other cases other than Fresno State. This is important for us, and I've seen this in the Central Valley in several farms. Variable rate irrigation. This is a technique. We work with a partner here, FarmIt.RX. They do the soil mapping and they do the design, and they place the sensors and they give you the recommendations based on your soil types. But you can see on the left is an almond orchard that was soil mapped, and we can see that sand stripe going by on the yellow. The green was the medium soil, and in blue the heavy soil. And here in the middle you can see that actually the irrigation system matches the soil type. Actually, this picture was taken right after an irrigation event on the dry soils, so you can see how it's wet. So your drip lines are matching your soil type, and you can irrigate by soil type. That would not be possible without soil moisture probes to manage that. That variable rate irrigation is a very important case. We've also seen some guys on table grapes, especially near the coast. This is in Peru, where they changed their irrigation strategy in order to avoid splitting. These guys were splitting, 50% of their grapes were splitting. So what they did is that when in a specific phenology stage, when it's turned into color, they changed their irrigation strategy and went from a low frequency, high duration to a short duration, very high frequency irrigation, keeping the water shallow, stressing the vine a little bit, what reduced their splitting by 50%. So they went from a 50% overall split to a 25% overall split, changed the whole business. Another example on walnuts, where we could see the grower before applying any irrigation strategy, right at harvest, he would just stop the water, not irrigate anymore, and then until the rains came. Well, the year after that, we started working on post-harvest irrigation and irrigating a little bit, keeping the moisture, especially for root development. And the results were incredible. In a 3-year period, the root development and the productive potential of those trees changed dramatically. This guy had a 30% increase in yield. Used more water, but that 30% increase in yield just basically changed his whole business. And then processing tomatoes, we've seen that deficit irrigation 30 days before harvest in order to improve solids, to send the tomatoes to the processing facility. So moisture sensors, very helpful for that. Avocado, in Chile, we did a research project where we put sensors and data control and witness blocks, and the results were incredible. With management, the irrigation, you can see there's a very nice rhythm of irrigation and a complete strategy around it. Used 50% less water, and the production was exactly the same than the witness block. And this was actually performed in 2 blocks, in case it was not random. We performed it in 2 blocks, and the results were the same. About 45–50% less water content overall, less water in the soil overall, same production. So as you can see, there are return over investments of using this kind of technology boils down to some water savings. It depends on each case. It depends. I mean, we've seen growers that don't save water, increase their water use by 10%, but increase their production so much that pays for all that cost. But in general terms, we see water savings, we see energy savings for the pumping, and improvement in yields that are very, very interesting in some cases when there's actions to be taken. And with that, I think I'm done. I went over a little bit. Well, we started a little bit late, so I'll put that on you, Daryl. We can't hear you though. I think you're talking, but we can't hear you. There you go.
Oh, there we go. So we did have a couple questions that I can probably take over from that. It's they're asking basically how we can set some different alerts and alarms in drop control when it's compared to soil moisture. So we can definitely do that. Also, they were asking about different ways to look at irrigations on drop control. So basically how we can view an irrigation coinciding with the soil moisture. And that's a feature that we actually just added onto the account. Fresno State's account actually on the olives does it pretty well, where we can see the actual irrigation events as it coincide with spikes in irrigation on the top chart, as well as ET and irrigations below that.
So you're talking about, well, right now the olives is running. We were not prepared, but right now the olives. So first thing, to answer the first question, right here when you log into the software, right here by the bottom, you have your alerts section, and you can just go here and add an alert. There's a lot of users here because this is a demo account that we use, but here you select if you want to do on the added, which is what I was explaining before, or if you want to do on a specific depth. So let's say the added soil moisture, then you select your threshold. If it goes below, this is in inches, not in percentage, but let's say it goes below 3 inches or above 6 for longer than 5 minutes, I enable this alert, and then I can select if I want an email, or I can just type my email right here. Or you can select an SMS or even a phone call. So basically you can here come in, set up your alert based on whatever sensor you want. You put your threshold, and the system will send you the alert through SMS, email, or phone call. The phone call is mostly used for frost alerts, but the availability is there. That was the first question. The second question, I didn't really get it. Was it where you can see the irrigation events?
Yeah, so how you can see the irrigation events that coincide with the soil moisture depth. So those blue bars right there, basically how to enable and how to disable them. So you just click that button.
Yeah, so I'm just gonna, for example, ask the system to show me the last month. It's gonna show me June. I'm gonna hit previews to look at the last 30 days. So right here, what we're looking at is, well, we just went through this, but we got the different depths. We got the added, and then down here in the bottom, we got ET and irrigation. There hasn't been any rainfall. But as Daryl was saying, you got the blue bars. It's showing you the irrigation event. So down here, it's showing you how much it irrigated. So let's say in this case, it was 0.48 inches, this irrigation event. And right here, you got the duration of the irrigation event. If you click here on this little drop, it will remove them from the graph if you don't want to see them. Or if you want to have more detail, you can click on the bar. And in the bottom, it will show you the start time, the end time, total volume, in inches, I just went with 30 days, and in gallons, and the average flow. And here actually I have a comment. And you can even hit on the link right here, and it will take you to the information of that specific irrigation event. So it will show you, okay, this irrigation event, if you want to look in detail, that irrigation event, it will show you, okay, it's an irrigation that started at 6, ended at 12. It was supposed to put 0.35 inches, it put 0.4 because it's running 199 gallons per minute instead of the 165, I think is the theoretical, 175. And here you got a little graph that shows you the flow over the time and the pressure. You can clearly identify, this is the pressure after filter, so you can identify the flushings. So here it allows you to understand more information, specific irrigation event, if you wanted to see what happened with that specific event. This farm is currently running right now as we speak. They're irrigating, they're irrigating everything actually. They're irrigating the almonds and the olives. But the olives that we were looking at right now, right here, This is where we're looking at. You got the pump start stop here. We got a soil moisture sensor here. We got a soil moisture sensor here. We got a water potential sensor here. We got flow meters, pressure, dendrometers. It's kind of our test plot. But here you can see if it's irrigating right now, based on the irrigation information. It started at 5:55 a.m. It's automatic. It's been running for 6 hours and 19 minutes at 195 gallons per minute average with an instant flow where the last reading was 198 and at 31 psi after the filter. And you can soil moisture, allows you to understand, okay, this is where we're at. This is the reading. This is the graph for the last 2 weeks. It allows you to, and it shows you in green because we are in that fairway, in that adequate position. So I don't know if that answers the questions, but there's several ways that you can get to irrigation information, either through the soil moisture chart. And then the other thing that's actually pretty cool about it is that you can actually see on the soil moisture chart itself, if let's say right here, we're looking at or the soil moisture analysis dashboard. Right here, we're looking at the last 2 weeks from June 4th to today. And here we can see that you can see the average soil moisture for each one of the depths. This is not in percentage, this is in inches. There's a way that you can convert that. But you can see that accumulated irrigation has been 1.93 inches in 87 hours and 45 minutes, barely any rainfall. So total, you got 1.93. And your accumulated ETC, where you can go change the KC value on that block, it's 2.61. Or so your real KC is 0.74 for the last 2 weeks. So there's different ways where you can get to the irrigation events, to the correlation, to the comparison between ET and soil moisture and irrigation, through different points of the software, depending on how you get there. If you get there through soil moisture, you can get into your irrigation event by just clicking here on your irrigation event if you want to go take a look at it. If you want to go to irrigation analysis, then you just hit on irrigation analysis and you go analyze the specific irrigation information, not soil moisture necessarily. And this now starts showing you, pressures and shows you total acre feet. Like again, this last 2 weeks for this block that it's olives, 19 acres, theoretical flow 175 gallons per minute with a KC value of 1. They haven't changed it. So it has irrigated in the last 2 weeks 1.93 inches, 3.14 acre feet, 0.16 acre feet per acre in 87 hours and 47 minutes. Pump started 6 times and it's been running at an average of 194 gallons per minute. So you can, depending on where you come from, what kind of information you can look at.
Gotcha. I think the last question that we had was for determining that low stress point for soil moisture, how agronomists kind of make that decision to where they know the low point. Like, do they have to go into a day of stress to where they know, okay, this is actually where my wilting point is, or how do they make that decision?
Well, there is no, not necessarily. Usually we recommend that you start off with the theory. I mean, you can technically download take a soil sample, take it to the lab, understand what soil you got, and that's going to tell you basically where your fill capacity is and what your available water or even wilting point is based on water holding capacity. So you can start off with a theoretical, but then it needs to be ground truth and it needs to be fixed based upon your crop, your weather. There's usually more than one soil type there. So the location of the probe, how far from the emitter it is. So yes, there is some trial and error. There is some field work that needs to be done in order to calibrate that reading. But to start off, you can start off by just, using your theoretical water holding capacity based out of the triangle of textures or here, actually, I have, let me look it up. Well, there's theoretical levels that you can start off, and we have a whole guide around that we can share. It's a presentation, and you can use those numbers to start off. But then you need to do that ground truthing for sure. because it will vary based on so many factors: root development, you know, if the season, if the spring was a wet spring, and you got roots that developed on the roads, right? And now you gotta control the roots on your berms. So there's so many reasons why you change those numbers and calibrate them to your field specifically. But there is guidelines to get started based on your soil type and the water holding capacity of your soil type. As I said before, like a clay will probably have a wilting point of around, 30, and then you'll have a sandy loam that will have a field capacity around 30. So, and a wilting point around 20. So there is some numbers that are theoretical, and there's guidelines for you to get started with that.
Perfect. Other than that, that answers all the questions that we've had. This is all recorded, so everyone in here is going to get a copy of the recording, and I'll try to send that out by the end of the day today.
Great. Thank you for joining, everybody, and staying a little bit longer. Again, if you have any questions, just get in contact with us, and we'll be happy to go over your data and check, or maybe even train you guys on a more thorough session.